Thank you very much. The way I will do this is as follows. I give you a quick motivation and introduce the work program, show you some highlights from our Austrian side of contribution to the annex, talk a little bit about some potential contributions to the EPBD, and summarize some of the comments I've made. A lot of times in the past years, we've seen smart grid examples that indicated that buildings have an impact on grid operation. Here you can see a Danish study that shows the so-called cooking problem. When people return home in the evening, they turn on the appliances, and this also follows if you introduce heat pumps and electric vehicles in the grid. With demand control, you can shave the peak. It does have some effects on the time before, the loads before and after. But what's clearly needed here is a building perspective in terms of how much demand control is actually available in different building types and operations. The organization of the annex is such as Søren Østergaard Jensen is the operating agent. We have 16 participating countries and they're very diverse disciplines. It runs about 2016 to 2019. Here's the website if you want to have a look at our ongoing work. The definition for energy flexibility that we're using is the energy flexibility of a building is the ability to manage its demand and generation according to local climate conditions, user needs, and grid requirements. We have it structured in about 3 subtasks. Subtask A is about definitions and context. We have common terminology and definitions that need to be defined, also market analysis in terms of user needs, etc. Subtask B concerns a lot of analysis that are taking place in the laboratories and also demonstration buildings and even computer environments. In Subtask C then, we address demonstration sites and user perspectives. There's a couple of living labs that are being monitored, and I want to come now to the Austrian side, show you a little bit on what is being done here. On the thermal grid side, there's a need for modeling the Austrian buildings. What you can see up here on the left-hand side, the heat pumps actually don't cover all the energy demands from buildings. So it's important to use projects like the Tabula database to get a better understanding of what the demands of different building typologies are. And of course, then develop different archetypes of flexibilities for these different buildings. This one here goes more into the type of contributions that buildings can provide for the grid. It's interesting to note that older buildings have more thermal mass, but what sounds as an advantage is actually a disadvantage because they cannot really stay off grid or without power for too long, whereas passive houses, for instance, are very lightweight buildings. They don't bring a lot of mass, but they can stay off-grid for a long time. So you get in a city a very mix of these buildings, and they actually need to So these buildings need to be modeled before you know what you actually have. The same thing, of course, in a more pointed way actually happens when you look at the rebound effects shown on the upper right side. We also looked at, or are looking at, the improvement gained from working with more complex information models. It's not natural to assume that just because we have more complex information models, we get better results, because particularly when we model the effect for smart grids, we have to model huge clusters. We find in our research that the minimum is 500 units that we need to model. So with that, we actually have some experience in one project where we modeled forecasts for a frequent building typology in Austria. This is a building with 6 apartments on 3 stories. As I said, we used a cluster of 500 units in Vienna, Austria, and for matters of simplification, equipped with electrical convection heaters, and we could find an improvement of more than 30% of DSM events working with more complex information models. We also work on the questions of integration of information models. There we have questions of validation of parameters and what kind of system architecture typologies we have available for validation that are actually feasible and affordable. We also discuss a contribution to the energy of performance in buildings directive of the European Union in terms of the smartness indicator that's being discussed right now. This is a rating for buildings, ICT and electronic systems for optimization of building operation and interaction with smart grid. It's in the so-called winter package. And the annex has a position paper out that details a proposal for a more physical data and simulation-based approach for quantification of services in use. And we also bring forward the idea of a standardization of the external penalty signal that enables the comparability of energy flexibility among different buildings. So to summarize, in Annex 67, a methodology for quantification of energy flexibility will be developed. We have work in progress that is filling in on missing knowledge of thermal building loads and information models for different building typologies of the Austrian building stock. And we conclude that Annex 67 work is also a contribution to smart readiness of buildings as per the Energy Performance of Building Directive. Here are some references for all of you who want to eagerly model things in detail. And thank you very much for your attention.